So hello everyone. In this tutorial, we are going to see the problem satisfiability of equality equations. This problem is of lead code and you are going to get the link to this problem in the description box. Okay, so what this question tells me in the form of this equation vector, okay, in the form of a list rather, that is named equations. I'm going to have a list of equations given for me, okay. These equations are given in the form of strings, in the form of string. Okay, how does each equation look like? Okay, so we will be having variables like a, b, x, y. These are the variables and it will be given whether, let's suppose I have an equation formed using a and b. So a can be either equal to b or it can be not equal to b. Fine. Each equation is of length 4. Each equation is of length 4. I need to check whether the series of equations given to me are consistent or not. That's what is my task. If they are consistent, I need to return true, else I need to return false. Okay. Now, what does consistency means here? Okay. Let's take some examples. Now, what does consistency means? It means correctness of the series of equations we have. Okay. Let's suppose I have an equation like a is equal to b. At the same time, there is an equation that a is not equal to b. Okay. So, if a is equal to b, if suppose I choose this equation to be correct, this equation, whatever is given, is not coming consistent. Why? Because a can be either equal to or may not be equal to, right? Both simultaneously. If both the equations given to me are simultaneously occurring, they cannot be together true. Okay. So such kind of thing we need to find out. Let's take some other examples. Let us suppose series of equation given to me. Let's say a is equal to b. Okay. B is equal to C, correct, and C is equal to A. Okay, this is given. So what we can say is that, okay, A is equal to B, that's true. Okay, B is again equal to C, and C is equal to A. Okay, so all are coming good for us. Let us have an assumption that value of A is equal to 1. Then as per this example, we can see that value of B should also be equal to 1 because A and B are equal. Now what is happening? Value of B is equal to C. So again C should have value equal to 1. And again at the end we are given that C is equal to A, which is true. So we are seeing that a cycle is forming, right, between A, B and C. If all are equal, we are having a cycle between these three variables that they have the same value. Okay. Now let's take some other example. So let's use the previous equation only and let's say A is given equal to B, B is given equal to C. Okay, and let's suppose it's given C is not equal to A. Will this be consistent? What do you think? Okay, now let's again go in the same manner. Let us say that value of A is 1. Okay, now value of B, let's suppose as per this equation, okay, we can again say that, okay, since A is equal to B, it's given, we can again assume that B's value is equal to 1. Fine. Okay, now it's given as per the second equation that B is again equal to C. So if I say value of C, if I take this equation to be correct, right, then value of C again comes out to be 1. But here, what is coming? C is not equal to A. Is that true? Is that true? So what we can say that, okay, these set of equations are not non-consistent because as per these two, the first and the second equations, we have all the values of A, B, and C should have been correct. But one equation tells me that, okay, C is not equal to A, but it is definitely equal to B, which is not possible, right? Because again, A and B are having same values. So if C is not equal to A now, we can say that, okay, these set of equations are not consistent to each other. Fine. Okay, now to how should we judge whether a set of equations are consistent to each other or not? Okay, that's a big question. Okay, let us go ahead and see. So let us take some other example to go for the final illustration. How should we solve this problem? Let me say that A is equal to B, okay, B is equal to C, fine, and let's say C is not equal to A. Again, let us have two more equation. Let's say X is equal to Y and Z is equal to again Y. let's say. These are the 5 equations given to me for solving. Now, okay, we say that A is equal to B, right? So, value of A and B, okay, they are all same. So, let me write it somewhere. A is, let's say A is 1, then B again has to be 1. There is no equation that contradicts the fact, okay, that okay, B's value is not equal to 1 or B's value is not equal to A. There is no such equation that contradicts this equation. So, we assume it to be correct, okay. And now if I assume B to be 1, then again C should have been 1, okay. And then C again, we can see that it is given C is not equal to A. That means one equation is there that is contradicting these two equations. So somehow this set of equation is inconsistent. Now how should we say that? Or how should we illustrate that? So let's do one thing. If between any two variables, let's say A and B, an equality sign is present, let us assume that they will form a graph, okay. A, B and C, right? They were all doing what? They are forming a cycle, right? Whenever value of all three was coming equal, we somehow connected them and tried that, okay, they are forming a cycle, okay. There is, it's not necessary that this particular thing, okay, this particular equation arrived when the set of equation was somehow like this. Sorry, this cycle arrived when set of equations were A equal to B, B equal to A, and C equals to A, right? Okay, yeah, B was equal to C here. Yeah. So this was the illustration. We have how we have judged the entire scenario in the form of graphs, and yeah, we have connected A, B, and C with each other. Okay. Now let us see how we can do it. Okay. How to finally solve it. So what we can say, let's suppose if there is an equality sign between two variables A and B. I say that okay, A is having an edge, a bidirectional edge towards B. Right? This is my illustration, or this is how I will be assuming this problem. If there is an equality sign between any two variables, I will say A is having an edge towards B. Similarly, we have B equals to C. So B is having an undirected edge towards C. Done. Okay. Now say, okay, I will just form the entire graph based upon this sign, equality signs, right? So we can see that if we are having these equality signs, these three variables are forming or coming inside the same component, right? They are coming inside the same component, okay. Again, if I say that x and y, right? If for these two set of equations x and y, I say that okay, x is having an edge towards y. Again, since z is equal to y, I say that y and z has an edge between them, and all the edges are bidirectional or non-directional in nature. Okay. Okay, so we have two components for our given set of equations. We have two components. One component lies of ABC, right? Another component consists of x, y, and z, right? These two components are there for us. So, okay, how should I judge them? Okay, so I do have this list, right, of equation, and I know that component between any entity, let's say ABC, can be formed if value of all of them are equal, right? A is equal to B and B is equal to C, then definitely A and C will be having same value. So a component comprises of those variables whose values are same, correct? Now what I can say, once I have all these components, okay, once I have all these components, let's suppose I name this component of ABC as component 1 and this component of XYZ as component 2. Once I have these components, okay, I will go through the equations once more, right? Okay, now the, let's say A is, let me write it better, okay. So yeah, let us have it again. A was equal to B, B was equal to C, and C was not equal to A, right? Again, X was equal to Y, and Y was equal to Z. Or yeah, it was Z equals to Y, right? And we got our components as A, B, C based upon equality sign only. I don't consider for forming any component, I don't consider non-equal signs. This won't be considered. Okay, how we will be utilizing everything. Just see for more. Okay. Now, okay, x and y will be coming in my component 2. Sorry, it's not xy, but it will be xy and z. So I say that okay, A lies in component 1, B lies in component 1, and C lies in component 1, right? Again, X lies in component 2, Y lies in component 2, and Z lies in component 2. And these all variables are forming a graph for me, right? Now, okay, I will go through the equation once more, okay? If value of A and B are same, they should have been in the same component. That's what my analogy is, right? Okay, A and B are equal. Are they in the same component? Yes, both are in component 1. That's true. Again, B and C, right? B and C. Are B and C both in the same component? Yes, they are in the same component because they are having same component values. Again, when the equation comes, let's say C is not equal to A. That means C and A should not be in the same component. But what we see is that after we have formed the components, we see that okay, both A and C are in the same components. So this equation is not going consistent. Okay, if this equation is coming inside my set of or list of equations, these A and C, these two variables shouldn't have been in the same component. Correct. So this is why my analogy is that okay, even if for any equation, even if for a single equation like this, I get that okay, this is unequal, they should have been the different component, and I get that both the values of components of C and A, they are what, equal. Then I say that okay, definitely this equation is wrong inside my list and the entire set of equations are inconsistent. It may again arise in some situation that okay, it will be given C is equal to, okay, yeah, okay, yeah. So with some other variables as well, it's possible. Okay, it's not the only case that C and A will be given unequal and C equal to A has occurred for us inside the list, but yeah, some other variables as well, X, Y, Z, uh, some other variables as well might be having the same inconsistency with them. So even if we got just a single equation that is not satisfying with the component structure for us, we will say that okay, entire set of equation is wrong. Okay, so how should we code? Let's proceed ahead. Okay, so let us start and let us keep a few things. First, let me have a map, okay, in which these equations are between variables a, b, x, y, right? So we cannot have more than 26 alphabets, okay, between which we can form equations. So I can have a map of char and with its mapping with an integer, and what it will do, it will mark that okay, this particular character a or b in which component it is lying, right? Okay, kept it. Okay, now I have to form some edges also, right? So let me keep map again, that okay, between, if I'm standing for a character, between what other characters, okay, it is having an edge. So I will keep a map for them all as well. So let me name it edges. Okay, now how many characters are there? Okay, for all possible equations we have formed the equation. Let's suppose in example 1, the entire set of equations are present between two characters a and b only, right? Not more. So all 26 characters may not be used. So let us have a set of characters for which I can say that okay, this is the set of characters between which I have some equations, okay, given inside these equations array. And yeah, so now let's form the edges. Okay, let me go through the equations one by one. So let me say that okay, from the 0th till the last equation. Okay, let me go and access them. What are the variables for us? Okay, let me keep them in, or yeah, let me store them in char variables x and y. Okay, okay, these two x and y will be storing between which two alphabets my equation lies. Okay, so yeah, so see, if I have an equation like this, a and b, a equal to b, then this is of length 4, right? So the 0th slot and the 3rd slot, the 0th index of the equation and 3rd index of the equation, it is having the set of, these two slots are having the set of alphabets for us, which among which the entire equation is getting formed. Okay, So what I will say, okay, that let x store whatever equation is having at the left hand side of my equation, okay, given equation. So equations of ith equation, okay, and its zeroth index, whatever alphabet it will be storing, let me store that inside y. And then similarly what I will say is that equations of the ith equations third index, whatever alphabet it is having, let me store that inside variable y. Okay, this part is done. Now there is a bidirectional edge, okay, between x and y. That's what is the analogy we have. Okay, so what we are gonna do, I can say that, okay, edges of x is having y, okay, is having an edge towards y, as well as edges of y will be having an edge towards x. Okay, that's what is the meaning of bidirectional edges. Okay, if there is an edge between x to y to x, we have the same edge. Okay, and when do we count this edge? When does it happen? If what we have analyzed in our previous illustration. When does it happen? When we have a sign of equal to between these two variables, right, x and y. Let's say there is an equal to sign. Okay, in that moment only I will be having an edge between x and y. So yeah, how to judge that? So what is the difference between two equal to's and a non-equal sign? That whatever is coming here, right, there is just a difference, that two equal to's are not equal to. These two are same. Okay, so this is my, inside my equation, this is index 1 and this is index 2. So index 1 will be differing. Okay, so what I can say is that, if equations of I and its index 1, this is equal to the equal to sign, then only I will be having these edges, right? We just copy it and paste. Yeah, this part is done for us. Yeah, one thing we have left. Okay, so what we can say is that, okay, these x and y are definitely a set of alphabets for us, among which the equation is getting formed. Okay, an equation at least is getting formed. So what I will do, inside the set I will be inserting both x and y. Okay, this part is done for us. So we have successfully formed the edges, or the structure of edges we want to have for our graph. Okay, using this loop. Okay, let's move ahead. Okay, so now what we can say, till now, how many components we have? No components, right? We don't know how many components are there. So let us say that, okay, initially I don't have the count, let it be 0. Correct? Okay, now what we are gonna do, let me have a BFS over all the alphabets we have stored, okay, using this edges structure, or the edges we have between any two alphabets. This entire structure we have made, and now I will go through our entire graph components one by one using BFS. So let me start accessing all the characters one by one inside my set. So what I will say, let me have an iterator. And using this iterator, firstly I will be accessing what is my current character, right? Okay. So if I dereference the iterator, I am getting my current character of my set. Okay. Fine. So if I am having a BFS approach, I should keep what? I should keep a map whether a particular character has been visited yet or not. Okay. Kept. This part is done. Now let us focus on the BFS approach. Okay. So I should say, okay, if, let me just check one thing. Yeah, this won't be int, but this will be character. I should do one thing. If suppose I am unable to find inside the visited map the present character, that means this character have not been visited yet. So what I should say, definitely whatever components we have visited till now. Okay, some in some other component this is lying. Okay, if I've till now visited 5 components, let's say, then in the 6th component we can say my current character will be lying. So let me just do one thing. I should count whether my character is yet has been visited or not. If it doesn't, okay, if suppose the count of inside the visited map we have for this character is 0, that means it doesn't have any, it have not been visited yet. So what I will say, let us increase the number of components we have. Okay, so let's not make it like this, but let me shorten up it, because we already have a components map. Okay, component map, so it might get a little bit confusion for you people. So yeah, what I say, okay, let us increase the comps part, and let me do one thing. Let me first mark it visited. Okay, so visited of, let's, my given character will be turning 1 now. Okay, that okay, I've visited it, fine. Because this is a boolean variable, this one will be translated to true, that okay, this particular character has been visited now. Okay, so let's move ahead. So yeah, since this is an BFS variable, so before marking it, let's do one thing. Okay, let's do one thing. Okay, we can keep the components part, okay, as it is, but we'll mark it once we start the BFS traversal. We'll mark it visited then. Okay, so yeah, let us have a queue for our traversal, queue of characters, and let me push my current variable or my current character that I have inside the queue, and I will say while there is at least a character to be visited inside my queue. Say till the time my queue is not empty, what I'm gonna do, I'm gonna just say that okay, let me have the front first. Okay, let me store it inside variable f, and that will be having the front. This part is done, and now next what we are gonna do, we're gonna mark it visited, right? Or before that, let me pop it out of the queue. Okay, queue dot pop, and I can say now visited of my front, let it be marked as 1. Fine, whatever character I was having inside this front, let me mark it to be 1, that okay, this particular character has been now visited. Now one by one, okay, with what other variables or to what other alphabets this particular character is having edges, let me traverse them one by one. So yeah, let us go for all those alphabets we are having inside the vector of characters. Okay, inside its vector, this character is storing inside my edges 2D vector. Okay, so yeah, what I'm gonna do, I'm gonna run for a loop, and inside my edges, right, edges of what, my current character f. Okay, and yeah, so yeah, this is also a vector, right, edges of f. This is a vector of what, a list of all those alphabets with which my current alphabet f is having an edge, right? So yeah, let me store it in some other character variable. Okay, so what I'm gonna do, let us have a character, let's say b. Okay, towards what other variable, or to my current character is having h towards what other variable, I will be storing that inside this variable b. So I will say edges of f of I is getting stored inside this variable b. Now okay, let's move ahead, and let's say if this variable v, okay, this f is having an edge towards v, and suppose if it is not visited yet, okay, if I say this particular variable have not been visited yet, so what I am gonna do, I'm gonna push it inside my queue, okay, and will involve it inside my BFS traversal. Okay, this part is done. One thing we have missed inside our BFS approach is, okay, we have marked this f visited, and now what we are left to do, in which component it is lying, right? So I will say component of f. This is my, at whatever component count right now, whatever comps variable value we have, at what component it will be lying, component number this. Okay, this is what my analogy is. So this marks for us the end of our BFS traversal. Okay, and we have successfully, using this BFFs, we have successfully calculated at what component a particular uh, alphabet, let's suppose any of the ABC is lying. Okay. Now, okay, let us go through all the equations one by one, right? Let us go through all the equations one by one. We'll just take it. Where is it ending? Ending here. Yeah. So what I'm gonna do now? Let me check all the alphabets one by one now. Okay. Or all the equations for the given alphabets one by one. So I say, let me have the loop again. And okay, let me have them inside characters x and y again. That okay, equations of, sorry, the ith equation zeroth slot. Okay, what it is having, and again ith equations third slot, what it is having. Okay, now again I will check if suppose that ith equations, yeah, at what index the equality sign will be lying, or for the non-equality sign will be lying, that will be lying inside the index number 1 for the ith equation string. Okay, so suppose this is coming equal, this is coming to be not equal to. Okay, then what we should say, this is coming not equal to, and I should check now if what is coming, yeah, if the component, right, component of x is equal to component of y. Yeah, if this is true, okay, and we are having an unequal sign between them, we can just return false from here, that this is not possible, there is something wrong with the equations we have. Okay, yeah. Now there can be one more counter as well, that okay, what if the reverse is true? Okay, if suppose equations of, though this is unlikely to occur for us, okay, very unlikely, but again I would just like to include that if suppose there is an equality sign between them and the components are not equal, which will not definitely occur for us, because we are always taking into the account that if we have an equality sign between any two variables, they will definitely lie in the same component. So this condition will never occur for us, that okay, there is an equality sign and what we are saying, their component is not equal, right? There is an equality sign but they are not in the same component. Okay, x and y will not be equal. So we can again say return false, but this will never occur. But still, I have included that for you for a little bit of visualization. And yeah, okay. Once we say that okay, nothing is returned false from the, after traveling or after visiting each of the set of equation that we have. If everything goes right, I will say return at the end. That's all. Let me try running this. Okay, so the first test case that we have, the initial test cases given for us, has been accepted. Now let me try submitting this finally. So yeah, we have got success for our solution. Okay, so the analogy and the way technique of BFS, keeping the components of all alphabets that we have, is completely correct. We can solve the question like this. So yeah, let's now see that okay, we have mainly utilized okay BFS for solving our question. Now see, there can be at most I say n nodes, right? N nodes, and these nodes are what? Alphabets. Alphabets. Now, how many alphabets at max we can have? 26, right? Not more than that. So each of the alphabet using BFS, I am visiting not more than once. Yeah. So I can say I am having traversal to all the nodes I have in big O of, I can say almost constant 26 times. Right. Now, if suppose there are n equation, right, and I am visiting each and every one of them to either check for the consistency. At the last, we have checked for the consistency and we have formed the edges, right? The edges graph that we have formed after traveling each of the n equations. What I can say now is that, okay, if I am traveling it, I am visiting each and every of the equation in big O of n time. Correct? So yeah, visiting the nodes of the graphs as well as all the edges, it costs me big O of n plus 26 time. Right? So this 26 is almost constant. We can neglect this. I can say the time complexity for my problem is big O of n, where n is the number of equations. Okay, fine. What's the extra space I'm using? Okay, what's the extra space? Let's say we have a complete graph, right? Complete graph. So in which again I have not more than 26 nodes inside my graph. Only 26, and for a complete graph, each of the alphabet, let's say A, it will be having an edge towards all other alphabets, right? B, C, D, every of the alphabet it will be having an edge towards. Okay. Similarly for all, B will be having except itself A till Z, right? It will be having an edge towards each and every of other alphabets. So I can say that, okay, 26 variables, okay, it requires space for 25 other alphabets, okay, to store them inside the edges list. Fine. So 26 into 25, this is the extra space I require to store the edges, okay, plus 26 I require for marking the components, plus 26 I require whether they are visited or not at max, right? This is the maximum extra space that I require. Again, they are of constant value. They are not of any they don't depend on any of the variable n, right? Where n is, let's say, the number of equations. Any of the nm they don't require. So I can say almost in constant extra space I'm able to solve my problem. Okay. So yeah, I hope you liked this video. If you liked, please like, share, and subscribe. Any of the doubts, you can put that in the comment. Okay. Thanks for your time.